So I'm going to go over question 8. Let me share my screen. Okay, so question 8 shows us two oxygen binding isotherms, where the percent of protein that's saturated as a function of the amount of oxygen. And one curve is for hemoglobin and another is for myoglobin. Zoom in a little bit. And we need to figure out first which curve is for hemoglobin. Now, what we know about hemoglobin is that it is allosterically regulated, which means that already oxygenated hemoglobin has a higher affinity for oxygen and binds it more tightly. And this would result in a sigmoidal or switch-like curve, where rather than a steady increase in binding, there is a switch-like change from low percent saturation to high percent saturation. So the hemoglobin binding isotherm is the one that has a sigmoidal or switch-like change in binding. Now, in part 2, we can consider the effect of BPG on the allosteric binding of hemoglobin to oxygen. Now, BPG is an example of an allosteric regulator, or allosteric effector. And it binds to hemoglobin and it stabilizes its T state while destabilizing its R state. So in the presence of BPG, hemoglobin has a lower oxygen affinity than it normally would without BPG. Now, what happens when we remove BPG? So since BPG typically stabilizes the T state over the R state, the T state is less stabilized when BPG is removed. And this means that hemoglobin has a higher O2 affinity overall. And so it would more readily undergo the conformational change from the T state to the R state. Now, since a lower concentration of oxygen is now required for the transition from the T state to the R state, the switch occurs sooner in the curve, and the overall curve shifts to the left. Now, in part 3, we can compare myoglobin and hemoglobin binding to O2 at different concentrations of O2. So, we need to determine why myoglobin is a poor carrier of O2. So let's think about what makes a good oxygen carrier. So a good oxygen carrier would be able to pick up more oxygen when the oxygen concentration is already high and drop off the oxygen to regions where the oxygen is scarce. So this means that in high oxygen concentrations, a good carrier must have a high fraction bound. And in low O2, it must have a low fraction bound. So we can calculate the fraction of O2 bound by myoglobin at 6 millimolar, the high concentration, and at 2 millimolar, the low concentration. So since myoglobin does not exhibit allostery, the equation that we can use to calculate fraction bound is simply the concentration of ligand over ligand concentration plus Kd. And we can calculate the fraction bound at 6 millimolar, and this for hemoglobin, or for myoglobin. Calculate fraction bound at 6 millimolar and fraction bound at 2 millimolar using this equation and the given Kd. And we can compare them. Now, if there's a significant difference between these two fractions bound, that would mean that myoglobin would be able to drop off and pick up oxygen like hemoglobin does. If there's no significant difference in these two fractions bond, then myoglobin would not be able to behave like a switch, and so it wouldn't function well as a carrier. So from these two values, we can determine whether myoglobin would be able to act as a carrier.